Beginning now. All right. Well, guys, welcome to Science of Diving. This is one of my favorite classes that we teach. This XR extended range are some really fun things, and there's some really big topics we can kind of go through in this. My qualification teacher, so I'm a Science of Diving instructor, of course. I'm also a decompression diving instructor as well. Decompression chambers expert, or not expert, but instructor, as well as an instructor trainer with SSI. So that's why I get to teach this. So let's just jump into this. We're going to talk a lot over tonight about physics and the basic ideas to set up the principles for everything else that we're going to go through. So jumping kind of into it, Adam, what do you think physics are?
Physics, I would assume, is just the natures of all the elements that we're dealing with, like air, oxygen, nitrogen, all the different things that computed into doing what we do, diving.
Absolutely. It's the interaction of those. That's a great way to look at it. So I love that you're already kind of getting the idea. It's to study the characteristics of the interactions of matter and energy. And so underwater, these various types of matter and energy that are important to understand. It gives us a better understanding how they affect us and the world around us as well. So physics often call for qualifications as well as quantifications, to be precise, as well as science. So we'll get a little bit into the formulas as well. So good job, though. So the biggest thing I want you to know is don't let the math of diving intimidate you. Physics is really just simply a way to scientifically calculate quantity and quality of what we're doing, right? So that we're able to be safe. So don't let it get overwhelming to you guys, because it's not. It's all pretty basic stuff. If you can do simple algebra, x plus y equals whatever, then the rest of this is really pretty straightforward. And so there is a saying that goes, unless there is a number, the truth is not known, right? So what we're going to do is help you find that number in a non-intimidating way. So one of the things that we like to kind of start getting the idea of is, when is a scuba cylinder empty?
So is it the technical term when you're meaning like when we're out of air, or are we talking about when we should be heading to the surface?
Nope. I just have a basic cylinder in my house sitting over here. When would I consider that cylinder just empty? Nope, nothing in it.
I guess at 0 psi in the atmosphere that you're in.
When the pressure is equal to 1 atmosphere pressure, or the atmosphere pressure it's in, or whatever.
Yeah, there you go. There you were. I could see you dancing it, and that's exactly right. When the exterior pressure meets the interior pressure. So it's for a simple enough way to put it. And so that would vary, right? We've all taken that bag of chips, and then we've driven over a mountain pass. So, Megan, what happens to that bag of chips if I'm at 5,000 feet? I drive to 10,000 feet of elevation.
It's going to expand. If you go right, it's going to.
Yeah, you're exactly right, because it has 1 atmospheric pressure in it, and we're taking away. Because of Boyle's law, as the pressure decreases around it, the volume interior increases. So now it's no longer equal. It's not as soft as it was. It's really going to be thick. So the same thing happens with a cylinder, right? If we take a cylinder at 1 ATA, that's interior 1 ATA, exterior 1 ATA, and I take it up to 16,000 feet elevation, and I open the valve up, what's going to happen?
You're going to have air.
Yeah, it's going to come out, right? So that's kind of one of the things we're dealing with, is the atmospheric pressure. So one of the interesting things is 16,000 feet is when we get to the point of 50%. And that might be a test question. And I'll try and throw those out once in a while as well. So if you take a sealed scuba cylinder that is empty at sea level to 16,000 feet, and we open it, we just talked about it. It expands because the exterior pressure is less, the interior pressure is allowed to expand, so we get air coming out. And it comes out to 50, it's literally 50% of what we had at at a base, right? So one of my favorite, as we try to talk about the idea of pressure and what we're dealing with, I was teaching a solo diving class last year, and I had a student with me, and I'm having all kinds of fun stressing him out, and we're at 60 feet. And I had a 30 cubic foot pony bottle that I needed to breathe off. It had, 50% nitrox in it. I needed to breathe it off because I wanted to refill it completely with 60%. So I get to the point, I'm just breathing that around, and we were just getting ready to do our ascent, and last last breath. There was nothing left in it. Now, luckily, I had a whole tank on my back, plenty of gas, no big deal, regular around my neck. So I just like to point out I was completely safe. And the goal was to breathe this off. So, but I left the regulator in my mouth and I went ahead and started heading towards the surface. I got to 15 feet. How many breaths do you think I got out of that from 60 feet to 15 feet?
Almost double what you had. So
4 breaths.
I got 3. You're really close. I was probably taking bigger breaths than I needed to, but so I probably could have gotten 4. If I was Megan, I probably could have got 4 or 5 breaths out of it, but I'm Benjamin with big lungs and I got 3, right? So that's one of the things that we're kind of talking about. This is the basic physics. This is how the world is interacting around us with what we're doing and what we're breathing. Now, this is one of the interesting things on a safety note for you with SSI and all agencies. This is why they encourage you, if you do run into an out of gas emergency, always leave your regulator in your mouth as you ascend, because as the pressure decreases, the volume is going to increase. You probably get a couple more breaths out of it. And that couple breaths could save your life. I don't know about you, but I can't hold my breath all that long. God did not mean for me to be a free diver. So I fully believe this. So in my case, if I'm at 60 feet and I've got to ascend to the surface, 2 or 3 breaths would probably mean the difference between me drowning and me surviving, right? And so that's why we do that, and that's exactly the idea. We kind of go through that. So let's kind of yes.
That made sense, because in like stress and rescue, they teach you leave their regulator in their mouth, because if they are out of air, that could potentially, like clicked then, I guess.
Absolutely. And so that's exactly why we do that. That's exactly why I teach it. So I'm glad that you remembered that. And so the trick now is to remember that in an emergency situation, of course, but the brain, well, for most guys, we're already on caveman brain, so it's not very hard for guys, but women are always thinking. So it's uncommon for women not to be thinking. At least in my case, I'm usually not thinking. And my wife see me sit on the couch for a half hour doing, what are you thinking? Nothing. She's like, no, what are you thinking? Nothing.
Because men have a nothing box. Women don't.
I have a nothing box. Absolutely.
Me and Meg talk about that all the time.
Absolutely. So let's kind of get a few ideas out of the way here, just so we have an understanding. So there's 3 terms we use in diving. The first one's going to be atmospheric pressure. We kind of understand that one already. You both kind of alluded to it. So that's the air pressure at sea level is known as atmospheric pressure. The common unit for atmospheric pressure in the Imperial Measurement System is ATA. So at sea level, 1 atmospheric pressure is defined as 1 ATA. Yep. Now we'll get into a little bit later why that's the 1 ATA idea is yes and no, right? At the atmosphere we're at, or at the altitude we're at, we're not at 1 ATA, but we will definitely get into that. So there's another term we use called hydrostatic pressure. Now, Megan, what do we mean when we talk about the hydrostatic pressure?
Oh, is that the pressure that it takes to change the amount of pressure? No, I don't know.
Madam, you got an answer for me?
Yeah, so the hydrostatic pressure is like the atmosphere above sea level that's pushing down. It's all about pressure. So it's like the environment that we're in pressing down on the surface of water. Hydrostatic is water pressure, so to speak.
There you go. You're getting there. You're absolutely getting. I can see the wheels turning, and I love that. So hydrostatic pressure is the weight exerted by fluid or water under the force of gravity.
Yeah.
So
that's
it's the
what
weight
I was trying to say. You just said it better.
I can see you getting there. You were thinking it, and you knew it. You just had to verbalize it, right? And that's kind of the trick with this class sometimes, as well as verbalizing the correct answer. I can see you get it, but I like to hear you verbalize it. So hydrostatic pressure comes from the weight of water excluding air pressure, and hydrostatic pressure is commonly expressed in pressure per unit depth, or PSI, right? So just to get a few ideas out of the way, 1 atmosphere of fresh water is 34 feet. 1 atmosphere of seawater is 33 feet. Megan, why is there a difference in those two?
Is it because of the buoyancy of seawater versus salt water? Like the density of the water, I guess? I don't know.
We're getting there. There's something in seawater that doesn't have it in fresh water.
The salt. So
exactly. So anytime we add anything to our little backpack, it increases weight, right? So as we add that salt to the water, it gets heavier. So because it's heavier, it creates more hydrostatic pressure. So we don't have to go as deep in seawater to get to that first atmosphere of 33 feet. In freshwater, minus the salt, it's not as heavy. So to get that same doubling in pressure at 33 feet, we have to go 34 feet instead. So as we look at this, there's a couple of numbers, and the more you go through SSI, the more you will see these numbers. So I'd encourage you, if you have a Post-it note and you want to go to your tattoo artist, these are 2 numbers to tattoo on you. Is freshwater exerts 14.7 psi divided by 34 feet, which equals 0.432 psi per foot for freshwater. So 0.432 is going to be a question at some point or more times throughout our training together. Saltwater exerts same 14.7 psi, but it divided by 33 feet, or 4.45 psi per foot. Make sense? Those 2 numbers, they come up a lot, so it's just easier to kind of get the idea to memorize 432, 445. 1 for salt, 1 for fresh. It's pretty easy to understand which one's the difference, right?
Yeah, it's just remembering them, like keeping them remembered.
Oh my goodness, believe me. When I was beginning in pro and trying to memorize a few of these key pieces, I wish somebody had told me, hey, memorize these 2 numbers because you will see them a freaking lot. And you will overall. Now, there's another thing we deal with, guys, called gauge pressure. You know, gauge pressure is primarily used for divers' information systems, and gauge pressure does not take into account atmospheric pressure. So in other words, the specific pressure being measured does not include the atmospheric pressure. The gauge is calibrated to read 0 at the surface and measure depth in feet seawater.
Okay, it's seawater.
Yes. All manual gauges are designed to read at feet seawater. Now, that's one of the cool things with moving over to a dive computer, like the Apex DSX, Asunto, Eon Core, Eon Steel, the Shearwater. Megan, if I remember right, you run a Shearwater, either a P1 or a P2. I've seen it. I can't remember if you run, which one you run, but
the Perdex, I don't know, whatever.
Yeah, they've got 2 versions. There's I've run both, the P1 and the P2, but that's one of the cool things with the Perdix, the Sunto, the Apex, most of those digital computers is there is a setting in there specifically set for one of 3 types of water conditions you'll be in: fresh, salt, or brackish, EEN 13, whatever. I've never dove the brackish water, so I've never had to use that. But it's specific, and what it does is it recalibrates all the rest of the algorithms based upon the type of water you're in, so it can give you a correct pressurization of what you're doing for how long NDL will actually last. Because if you think about that for a moment, your non-decompression limits will vary based upon depth, of course, but at that same depth, you'll get a longer NDL in freshwater than you would in seawater because you're not under as much pressure. Now, while it's pretty slight, as you get deeper, that variation increases dramatically, but it does increase, right? Because if I'm under more pressure, then I'm going to uptake more nitrogen. If I'm under less pressure, I'm going to uptake less nitrogen. And so that's one of the cool things that your computer will do for you. And one of the great reasons to have a computer instead of using a paper table is you're able to accurately measure the weight of the water, the atmospheric pressure that you're diving at, as well as the gauge pressure corrected for salt or fresh water. Make sense?
Yep.
And if I'm going too fast or saying things and you need me to re-explain it, please let me know. Now, there's the last kind of concept we got to get through is the absolute pressure. This one's a super easy one in my mind. Megan, what do you think we're talking about when we talk about the term absolute pressure?
Like the total pressure?
Yeah, exactly. It's right in the name. And I always love when the people are like, is it the water pressure? Is it the air pressure? It's the all pressure. It's the absolute, the total on it. So I love that you got that right out of the bat. So the term absolute pressure is used to describe the total pressure exerted on an object or you, the diver. So sitting on the surface, you are experiencing 1 atmosphere of pressure, the weight of the atmosphere, everything around us. So as you descend, there's an increase in the pressure due to the additional weight of the water, the hydrostatic pressure. So the absolute pressure is a sum of the atmospheric pressure plus the hydrostatic pressure. So it's all the pressure around you. Make sense?
Mm-hmm.
All right. You guys are crushing this and making my life easy today. There's a couple of definitions that wants me to kind of go through. I think you guys pretty much have an understanding of Celsius and Fahrenheit. Understanding Kelvin, unless you're going to get extremely scientific, it goes through Kelvin and Rankins. Those are really cool if you really want to figure out overall volume of a tank. But if you're anything like me, and I'm into the science, I will tell you right now, I love the science. I love the math. I have not once, not ever needed to determine the exact cubic feet of my tank by determining the Rankine degrees of the current air temperature. Not once, not ever. So if you don't mind, I'll skip that. You can certainly read it. I don't believe there's any really key questions on that. Adam, you are a super stud when it comes to math and feet, yards, and miles, things like that, because as a roofer, I imagine that's pretty important. So if you don't mind, I think we'll probably skip explanations of distance and length and area. I bet you could probably explain how to figure the area of something better than I could. So
I don't know about that, but I do understand some of the basics.
I would bet you've got a pretty good understanding. So if you don't mind, we'll skip some of those basic stuff because I think you guys are pretty smart and don't need me to explain how many inches in a foot. But understanding gases related to what we're doing. Yeah, the gases are pretty important to understand, right? Yeah. And so overall, as we kind of dial through this, nitrogen, what we're breathing right now, is about 78.08% nitrogen, right? We're breathing about 20.94% oxygen. And the rest is made up of like almost 1% argon. Around, I guess if you're in LA, maybe it's like 18% carbon dioxide. But here where we live, it's 0.03% carbon dioxide. And then there's other gases out there that Adam produces after going to Filiberto's that are 0.02, right? That we just want to talk about that when he's off gassing, right? It happens. It happens to all of us. Birds do it, the bees do it, boys and girls both do it. So we'll let that go. But for today's class, we're just going to round those up, and we're just going to say nitrogen is 79% and oxygen is 21%, if that's okay. Yep. So for our discussion, we talk everything is going to be at 1 atmosphere for pressure, which is sea level, and everything's going to be 79.21, just to make your lives easier. If you'd like, we can certainly get into the exact science of that and make the math harder. But if it's okay with you, we'll just keep it simple for now.
Simple is good. That's kind of what we've been using, and it's how we understood it, because we've already been through the nitrox class. We understand
absolutely
all the basics when it comes to that.
Absolutely. So one of the big laws that and we're going to go through several laws, and there's a couple of them that are really kind of my favorite. The Dalton, Henry, and Boyle are kind of my favorite laws to go through because they actually impact us on a regular basis. Boyle's law is pretty simple. Boyle's law basically is the relationship between pressure and volume. That's all it really is. As pressure increases, volume decreases. It gets squished. As volume increases, what happens to pressure?
The pressure gets bigger?
Yeah, it goes down. So as we have more volume around it, or more pressure around it, we have less volume. If we have less pressure around us, we have more volume, right? Things get expanding. Right. So as pressure increases, volume decreases. As pressure decreases, volume increases. It's an inverse relationship, and it's pretty straightforward. And so I'm going to show you the slide. I hate this slide because I think they could have done so much better. They could have done anything that would have been better, and it helped people understand this. So gas density, not lung size. And what they're trying to show you with this is in free diver mode. So when you see this chart on the right-hand side here, realize that they're trying to tell you free diver mode, not human mode. So when you go down, your lungs stay the same size. Your hand stays the same size at depth. Your feet stay the same size, so do your lungs. Unless you're a free diver, because you're holding your breath. And holding your breath is bad, right? But overall, if we had a 1 cubic foot balloon at the surface at 1 bar, we know that if we take that straight directly down to 10 meters or 33 feet in the ocean at 2 atmospheres, we reduce it by 1/2. We go down 1 more, we reduce it to 1/3 and 1/4. And what it literally does is it halves each time. So 1/2, 1/3, 1/4, and so on and so on. So what we're trying to tell you is as Boyle's law, there's not less gas in this balloon. What's happening is the molecules between it are getting squished. And so the way I like to think of it is, oh, there it is like this. Let's see. I have a teacher's aid just for you guys. That's not actually true, but I like to say, like to make you think you're special. So here's what's basically happened. Here's the air we're breathing, right? And I love this analogy because the darker blue can represent the oxygen. The lighter blue can represent the nitrogen, right? And yes, this is a sponge from our sponge drawer. I took the liberty of cutting one up. So what happens at the surface? It's all nice and together like this. But what happens when we go down to 33 feet is it gets squished. Megan, is there less sponge?
No.
All we're doing is we're taking the molecules between the spaces and we're compressing those. The molecules of the cells of oxygen are not getting less, but the space between the molecules are getting less. And the same thing happens. So we get down to 66 feet. Now we have the same equivalent of 3 molecules of air, of the gas we're breathing, in the same space as we had before because it all gets compressed and squished together. And eventually we go down more and it gets squished even more. So all we're doing is removing the space between, compressing everything else out, and that's how we come up with our partial pressure idea. And we can thank Mr. Boyle for that as well. So Boyle's law gets pretty straightforward. Pressure 1 times volume 1 is equal to pressure 2 times volume 2. That's all we're trying to say. We get into it. We get a lot more complicated than we really need to do. So overall, there's a couple different laws out there we can get into. We can certainly talk about Gay-Lussac's law, which is also referred to as Amaton's law, which talks about the given mass and varieties of the absolute pressure of the gas as well. And it gets overly complicated from there. But a simpler definition of this for you guys is Boyle's law is directly related to pressure at a constant temperature. An interesting story for you. Good old Boyle was a Scottish physicist in the late 1600s, early 1700s. And how he figured this out is what he was doing is he was putting a snake in a sealed container on a string and throwing it into the ocean, which makes me question completely the sanity of all Scots, but that's what he did. And he pulled it up too fast. And what happened is as he took the cap off, he discovered that the snake had a tear of blood coming out of his eye. And he realized that, wait a minute, there must be something happening with pressure. So he went on to theorize the idea that there's a direct relationship between volume and pressure. Now, he didn't talk about at a constant temperature. That was not Boyle. That was actually Marriott. And Marriott, about 8 years later, was a botanist in France. And he's the one that, through the study of plants, was able to determine, wait a minute, gas and pressure at a constant temperature. Because if we change the temperature in a boiling pot, what happens to the volume, Adam?
In the boiling pot?
Yeah, what happens to the pressure in there? If I put a sealed pot, a pressure pot of water on the stove, and I heat it up, what happens to the pressure inside the pot?
It just builds.
It goes up, right? There's a lot more pressure, right? It boils out, and as it cools down, there's less pressure, right? Pressure and heat. So it was Marriott that came up with the idea that everything has to be at a constant temperature. Pretty straightforward, right? Pretty simple. So we look at this and we think, oh gosh, seems common sense. So if you're in France or in Europe, they don't call it Boyle's law, they call it Marriott's law because Marriott discovered the constant temperature. Now we've kind of combined them overall. So just remember at a constant temperature. Now we start getting complicated in the reading material, and all of a sudden they want to pop out and they want to start talking about Gay-Lussac. Now the cool thing about Gay-Lussac is it's basically Boyle's law, but he's just saying that as the pressure increases, the volume increases. As the temperature increases, the volume increases. As the temperature decreases, the volume decreases.
Which is when that affects us sometimes when we're diving in cold water or like the hot pots. Absolutely.
We've all seen our tank pressure go up and go down as well. It's definitely one of those things to be aware of. But that's all Gay-Lussac is trying to tell you is that, hey, dude, if you have a sealed pot and you raise the temperature, the pressure inside is going to go up. If you cool that same thing down, it's going to get less. That's all Gay-Lussac. It sounds super complicated when you start talking about it, but that's all Gay-Lussac is trying to tell you.
Okay.
So there's your deep explanation of Gay Luss's. It's another side, in my opinion, of Boyle's law. Make sense?
It
Just with
does.
the temperature variation.
Yeah, he's talking. He says basically it's just a pressure variation based upon temperature, but it's just in my opinion, it's just another variation of Boyle-Marriott overall, because we're still talking about pressure and volume at a constant temperature. But if we just change the temperature, now we've just said, instead of it being Boyle's law, now it's Gay-Lussac's law.
Okay.
Go figure, right?
Yeah, it's just adding another element to the mix to say whose law it was versus not.
Exactly. So it really all comes down to ideal law, right? Ideal gas law is what we kind of deal with. But how this looks with gas is that we talked about a moment ago with our little sponges, that as we increase that pressure, we take the one molecule of air, 79% nitrogen, 21% oxygen, we take it down to 33 feet, it compresses. Now in that same space, we have the equivalent of 2 molecules of air. So the way we'd look at that is instead of saying 2 molecules of air in the same space, we'd say that the partial pressure of each one of them doubled. So now the partial pressure of oxygen, instead of being 21% like we see at the surface, now it's the equivalent of 42%. And nitrogen now has the equivalent of 158%.
Mm-hmm.
That's how we look at it. So I want to kind of introduce something to you guys. And this is a little bit more of an advanced concept, but here's how we kind of look at it. The density kind of increases as we go down. We've got their depth in meters here, 10 meters, 20 meters, 30 meters, 40 meters, 50 meters. But if you notice, I've added a little extra to our chart here. What I want you guys to kind of get the idea of is that as the partial pressure of that nitrogen increases, it starts creating a narcotic effect.
Right.
That is not good, right? And so at that point is roughly about 70 feet is where we want to start getting the idea that, wait a minute, nitrogen can cause a negative effect because of the partial pressure is too high. So as you start getting that idea, when partial pressure of nitrogen starts rising above 237%, we need to start watching out for that and being aware that nitrogen is going to start causing a negative effect. It's something we don't talk nearly enough of. And there's also another thing we're going to get into a little bit later called gas density. But I want you guys to start just kind of visualizing. We talk about oxygen becoming toxic, but we don't talk about nitrogen narcosis nearly enough, in my opinion. So just kind of get that kind of programmed into the atmosphere, if you would, and it makes your life a lot easier.
Absolutely.
And I want you guys to be safe. So the golden rule of diving, never hold your breath, is tied to Boyle's law. So Boyle's law basically, says that as pressure decreases, volume increases. Well, if I hold my breath and I've got 2 basic balloons in my chest, they're going to continue to expand. It only takes 4 total PSI for your lungs to burst and cause one of our dire arterial gas embolism, metacymal emphysema, subcutaneous emphysema. It only takes 4 PSI for that to happen. Now, we talked a minute ago about the pressure variations, and we said that the pressure variation per foot in the ocean is 0.445, right?
Okay, yeah.
How many times does 445 go into 2? 0.445 go into 2? About 4 times?
Yeah.
Yeah, a little bit more.
5.
So what I'm telling you with that is that you can ascend by just over 4 feet and actually cause a rupture in your lungs by holding your breath. Now, be it honestly there, you have to hold your breath and take and really try to get there, but you can see, and to get that 4 feet, other than that, at midpoint, maybe it takes 5, 10, 15 feet, but it can happen. So be aware of that. So that's that golden law of always breathe is absolutely tied to Boyle. Now, there's another law. Go ahead. I'm sorry.
It's that concept, like for somebody running out of air and then panicking, rushing to the surface while they're holding their breath.
Absolutely. Always be breathing, always exhaling as you're heading to the surface. And it's one of those really interesting things with free diving. If you notice, when the diver goes unconscious, or is about to go unconscious, they never give the diver air at depth for that exact reason, because they'll cause a lung rupture. They pass out while breathing, and they stop breathing. They can't exhale the air. They can actually cause a lung rupture. So it gets really, really dangerous.
Yeah.
So now there's another law out here that we're going to talk about, and you may have been wondering who this guy Dalton is, right? Dalton's law. Have you read, Megan, did you come across Dalton yet in your reading?
Yeah.
Okay. Dalton is super easy to understand. He is the law that calculates partial pressures. He's the one we have that figured out how to calculate maximum operating depth and best mix, understanding partial pressure. All Dalton law really is trying to tell you that no matter what happens, 2 + 2 always has to add up to 4. If we double that and do 4 + 4, it has to add up to 8. That's all he's really telling you, is that the sum of all the gases have to equal 100%, unless we're at 1 atmosphere or 2 atmospheres, which that means they'll have to add up to 200%. If we're at 3 atmospheres, they have to add up to 300%. All he's really telling you is it's a very simple law. So, but overall, it's extremely important. So understanding the basic ideas of this are extremely important. And you might have come across Charles' law as well. Charles' law is basically telling you that if the pressure of a gas is constant, then the volume of the gas varies directly with temperature. Sounds a lot like Gay Lussac to me, right? Yeah. These guys all were doing the same thing and talking in a circle. If you'd put them in, I feel like they should have just got married, because they would have made one complete couple, right? Overall. So Gay Lussac and Charles are pretty much the same guys. They're just talking about volume versus pressure. It's all related to heat, right? But overall, Dalton is our big way to explain this. So the laws you're going to come across are going to be, first one is going to be Boyle's-Marriott. Here's how everything you need to know right here. Boyle's-Marriott is pressure and volume. So when you think about Boyle or Marriott, you want to think the balloon and going to depth and the outside pressure around it. Easy enough?
Yeah, Boyle's makes sense.
Charles' law, you want to think pressure and temperature, or think of boiling pot. And so the pressure in a pot against the lid. So that's what Charles is trying to tell you, is as the temperature goes up, it's going to push that pot lid away. Gay Lussac is volume related to temperature. So think hot air balloon. This is the expansion of the air, or the volume of the air as it expands. That's all he's trying to tell you. It's just volume related to temperature. So if you think about hot air balloon, you're good to go, which very similar to the idea of Charles. Now there's another one we haven't really talked much about that, but we're going to get into, and Henry. Henry is one of us as cold water divers. We really need to understand Henry and deal with Henry. So Henry is the gas dissolved in a liquid. So the gas being the air we breathe, the liquid being our blood. So Henry's law talks about how, as we breathe the gas in, it goes into the bloodstream. So think like this. Think the Kool-Aid crystals in a pitcher of water. Megan, I imagine you've probably made more than your share of Kool-Aid for the kids, right? Hopefully without poison in it. Just kidding.
Yep.
Although I'm sure that thought's crossed your mind more than once.
Yeah.
It's thought. I understood exactly why some animals eat their young at times with my kids. Absolutely. What are you doing, right? So as you get that nice big crystal pitcher, Megan, and you pour that packet of Kool-Aid into it, how fast does it dissolve if you don't do anything?
Not very quickly.
How fast does it dissolve if you put a wooden spoon in it and stir the crap out of it?
Quickly.
Exactly. That's what Henry is trying to tell you, that the gas will dissolve as we stir it faster. As the agitation of our heart, how fast our heart beats, the gas will dissolve more quickly into our blood. Now, he's got one little caveat on there that's really interesting for us as cold water divers, is that cold gas will dissolve more quickly than warm gas. And that's because of the density. It's able to get in those little spots more easily. So those are the two things. So Adam, we as cold water divers, why is it important to understand that as our heart beats faster, gas dissolves faster into our bloodstream.
Why is it important?
Why is that important?
Because when we're in cold water, we need to take extra precautions when we're ascending so that we off-gas all the gas that we're taking on when we're at depth.
Yeah. How about this, though? How much heavier is your gear when we go driving in dry suits versus when you go in your thin wetsuit in the Caribbean?
Sorry, say that the question again.
How much heavier is your gear in cold water versus warm water?
Oh, I'm assuming there's a little bit more weight to it just because you're putting more gear on to stay warmer. Aside of, just for wetsuits and dry suits alone, I guess the weight's substantially more. If you're just
absolutely, you need more weight to get down. So that's one part of it, right? So as we're putting a lot more gear on it, if I carry a 100-pound wreck up a mountain, my heart probably beats faster than if I carry nothing up a mountain, right?
That makes sense too.
So as effort increases, my heart's going to beat faster, right? The other part of that is in cold water, my body's going to try and stay warmer, so my heart will beat a little faster as well. So there's two things we need to be aware of as cold water divers that are extremely important. Our heart's going to beat faster because the gear is heavy, and we're trying to stay warmer. Now, as we think about that realizes that the gas is dissolving into our bloodstream more quickly. Now, Megan, is part of that gas something we need to be concerned about as it's dissolving into our bloodstream?
Yeah.
What part of that is concerning?
The nitrogen.
Ding, 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 ding. You win the prize today. That's exactly right. So as we dive, nitrogen absorbs into our bloodstream and into our tissue compartments. And there's theorized that there's 16 of these tissue compartments, right? So if it's absorbing faster in our tissue compartments because of the agitation, because of the cold, and because of the work, then we have more gas that has to come out, right? Right. So as we think about that, how would that affect things like ascent rate or safety stops?
Longer safety stops to allow that to off gas.
Absolutely. Maybe cut our dive times down a little bit, maybe slow our ascent rates a little bit, and absolutely give ourselves more time out of the water, more time at the safety stop to allow that nitrogen off. So it's extremely important when we start doing things like cold water diving to make sure we take it. That's all Henry's trying to tell you, is that as you breathe faster, as the heart moves faster, and as the gas gets colder, you're going to take on more nitrogen. Yes, sir.
I understood the nitrogen. So I read somewhere within our reading the last few days that nitrogen doesn't absorb the same way as oxygen. What was, enlighten me on that part? Because I know that, like, obviously it goes into our body, so we have to off gas it, but help me understand that part again, or is that?
Oh, no, that's absolutely. No, I love the question. So nitrogen is a free radical. Oxygen will bind as it goes through the alveoli in our lungs into our veins, into the arterial gas network. What happens is it binds with the hemoglobin.
Okay, now I remember. That makes sense. And nitrogen does not.
And nitrogen just passes straight through. Now, interestingly enough, here's a couple of interesting facts you may or may not know. The alveoli have a blood barrier, and they only allow about 10% of the oxygen to pass through the system, but they let all of the nitrogen come through. Pretty interesting.
That is interesting.
So here's where it gets more interesting. So let's expand on that for just a moment. At the surface, it's letting 79 particles per whatever come through the alveolar network into the bloodstream. At 2 atmospheres, 33 feet, now it's letting 158% come through. At 3 atmospheres, 237% coming through. Whereas the blood barrier, the hemoglobin barrier at the alveolar is still only letting 10% through.
Okay.
So kind of interesting, huh?
It is.
So that's one of the cool things with when we use a higher percentage of gas as a decompression blend. What happens is it's like cutting the freeway off on an in and out of a city, right? What we're doing is we're not allowing as much with a higher percentage of oxygen, not allowing as much nitrogen to come into the city, but we're letting all the nitrogen come out. So that's one of the reasons it's nice to use a decompression blend. And that's what decompression divers do. When I go out and do these really big dives where I'm using a bottom and a travel gas, and then I use a different gas for decompression, that's exactly what I'm doing. Is I'm cutting off the inbound lane for nitrogen, and I'm expanding the outbound lane for nitrogen. So I'm allowing a lot of nitrogen to come out, but not as nearly as much nitrogen to come back in. So that's why accelerated decompression is such an amazing thing.
Yeah, and then you're able to do that, but you can't do it at depth. You do it like not deep, but you can do it at a shallower depth. In order
you do absolutely because the partial pressure is
rich
maximum operating depths. You got it. You're gonna make my job super easy. That's for sure. So that's kind of what Henry's Law is all about, right? It's how that is coming in. That's all it's trying to tell us. And then finally, Dalton, our good friend Dalton, tells us when we have a mix of different gases like air, each gas pushes on things around it with its own strength. The total pressure exerted by a mix of gases is equal to the sum. And I always kind of look at that thing, and when I think about that, I'm like, well, no, duh. So if I add 2 and 2, it always equals 4, huh? Right? I love these guys with their complicated explanations that really come down to 1 and 1 is 2. Did you know that? Huh? I'm a genius because I explained it to you really complicated way. That's all he's trying to tell you is the sum of the gases have to equal the total. Wow. So, and we use Dalton to understand partial pressures of gas mixes, example, best blends, and maximum operating depths. That's where we use those.
Okay.
So that's kind of all the laws and what they're really trying to tell you. Here's where we use them. Boyle's-Marriott is used by divers to determine the amount of usable gas in a tank during a dive. That is the best place and really the most comprehensive place where you can use Boyle-Marriott is how much gas do I have in a dive? So Megan, if I have 80 cubic feet of usable gas at the surface at 33 feet, how many cubic feet of gas do I have?
40.
Ding, ding, ding. You guys are experts at this. So literally, if I have only 40 cubic feet of gas at 33 feet, does that mean I can use the tank as long as I would as if I had it at the surface? No, right? If I can breathe on an 80 cubic foot tank and it takes me an hour at the surface sitting in my lounge chair watching Big Bang Theory, in theory then, without any additional effort, if I'm still watching Big Bang at 33 feet of seawater, I should only get a half hour of time out of that, right?
Yeah.
So that's reasonably important, especially when we start getting into those deeper dives, to realize that I've got 80 cubic feet at surface and I can go through that in an hour. But if I'm at 132 feet, I'm not going to get as much time out of that tank, right?
Exactly.
We get 1/5, right?
Mm-hmm.
Ding, ding. There we go. So that's all we're trying to tell you is Boyles-Marriott, that's the time we're going to figure out how much usable gas is in our tank, right? And then we can also get the idea that, hey, wait a minute, if I leave that tank out in the sun and it's 90 degrees outside, it's baking in the sun, right? And then I suddenly jump in, Yellowstone this week was 38 degrees. I jump in the lake at 38 degrees, I'm going to have less gas in the tank.
Yep.
And we can thank our good friend Gay Lissick for that, right?
Not necessarily, but he understood it.
Yep. Charles or Gay Lissick, you can thank one of those two guys for helping us understand that if it's hot, there's more. If it's cold, there's less.
Yep.
And as guys, we understand when cold, there is less, right? We have an intricate knowledge of that one.
Yep.
Take that however you want. So that's what Boyle's trying to tell you. So Charles' law, we use that to understand when to stop and let a tank cool when we're filling it. So Charles' law, so if I take a tank, and Megan, you've been in the back room when we fill the tanks, what happens to those tanks if I fill it real quick?
They get hot.
They get hot. So we got to let them cool. So we get down to the real pressure, and then we can fill it back up and let it cool and fill it back, get it up to the correct point. That's where we use Charles, is how and it gets hot, stop, let it cool down so we can fill it again. Because if we don't fill it again after it cools down, there won't be enough gas in it, right?
Right.
That's where we use it. Gay Lissick, that the effect of temperature around us when we get ready to dive. So think of a tank sitting in a hot car or a tank going in the cold water. We've all dove Belmont in January. We've had that nice tank, and all of a sudden we jump in, and I have actually done a 5-minute dive at Belmont and had a negative sac rate. True story. My poor little Perdix looked at it, was like, your sac rate is negative 3 psi per minute, and which means I was putting gas back in the tank as I was breathing. Right. That's all we're trying to tell you.
Just because it got so warm when you got back, and yeah, that makes sense.
Exactly.
Kind of funny.
So Henry's law is just the law of. I'll give you 2 new terms. And I'll throw these out a few more times. Is perfusion and diffusion of nitrogen in the body during a dive. That's really what Henry's trying to explain to you, is how the gas perfuses. I always want to say profuses, but it's not. It's perfuses into the body. That means it's absorbing in, and diffuses means it's coming out. So where we can think about that is, here's an easy one. If I had, let me just throw crap around here. So if this was a bottle of Coke and it's sitting there and there's no bubbles at all in this pressurized bottle of Coke, that means everything is perfused into the liquid. If I open the top, we see those bubbles. That means they're diffusing out of the liquid. That's exactly what's happening in our body. Is as we start to come up and the water column, ascend in the water column, the nitrogen is diffusing out of our tissues and becoming bubbles. As we go down, that nitrogen is perfusing into the tissues.
Okay.
Easy enough. And then finally, Dalton, our good friend Dalton is our best friend when it comes to understanding the best blend of gases or the maximum operating depth for our dive for a gas. Those are the times we use those laws and why we'd use those. Make sense?
It does.
So just a couple of review terms. These when I do these review terms, they may or may not, but they are test questions as we go along. So start with Megan. We haven't picked on Megan for a few minutes. Megan, nitrox is a term used to describe breathing gases made of oxygen and nitrogen with mixes. Let me start that again. Nitrox is the term used to describe breathing gases made up of oxygen and nitrogen mixes with the oxygen percentage being higher than what?
Higher than 21%.
Exactly right. Good job.
Oxygen.
Exactly. Now, the interesting thing is truthfully, nitrox is any blend of nitrogen and oxygen. That's the true definition of nitrox. But for the purpose of diving, we'd consider nitrox to be any blend with oxygen greater than 21%. All right. Now, just a review question. This comes back to us from nitrox. Adam, the percentage of oxygen needed in a gas mixture for a diver to maintain consciousness at sea level is?
So the amount of oxygen they need
To remain conscious.
I actually don't remember that, but I'm assuming it's 21% is my guess.
Actually, 16%.
Okay.
To remain conscious, to remain alive is 10%. Any gas blend that has less than 10%, you will die. 16%, you'll pass out.
Okay. Okay, I don't remember reading that, but I'm sure I did.
It should be in the mix in there somewhere. So I'd like to do a couple just kind of basic calculations, if you guys don't mind.
Sure.
Let's see. All right, let me get over to. So I'm going to share my screen, and I just want you guys to understand this. But the good news is, if you guys have your My SSI app, I'm going to show you where to find this as well. So Dalton's law and practical application for best mix of nitrox is done like this. If a diver wishes to make a dive to 115 feet, what is the best mix of nitrox for this dive? Here's how we do that. 115 feet is the depth. We divide that by 33 feet FSW. Megan, what do you think 33 FSW means there?
Fresh or seawater.
Yep, feet seawater.
Salt water. Salt water.
Yep, feet seawater, feet salt water. So that's what we're coming up with. So we divide those two, 115 by 33, we equal 3.48. Now remember, that's the hydrostatic pressure. So we still have to make that absolute pressure, which means we have to add 1. That's right. So 3.48 plus 1 is the surface addition of the ATA, makes 4.48. With me so far?
Mm-hmm.
Okay, so remember, we as divers want to stay at 1.4 partial pressure of oxygen or less just for safety. So all we need to do is we need to take that 1.4 working load of partial pressure of oxygen divided by our actual atmospheric pressure, which is 4.48. That should equal out to 31%. Well, good news is, do you guys happen to have your My SSI apps handy?
Yeah, I've actually fallen wrong, so
awesome.
At least,
if you guys would just for my edification, would you mind opening up that SSI app for me?
Mm-hmm.
At the bottom, it says More, and then you should see a green button that says Tables. It looks like a little Excel spreadsheet.
Just a second, I have to get out of the course. So More, okay, and then where?
To Tables. Megan, do you see that?
Tables.
Awesome.
Maximum
Go to Tables.
operating depth table.
We're looking actually for best gas mix table. That's the one we're on currently.
Oh yeah, I see it.
And you want to open that in English Imperial. You're welcome to open it in metric. I can do metric too. If you look at that on your SSI app, that may look just like the little table I have here on the right-hand side. So we can check ourselves. We want to do this dive to 115 feet. Well, we can go over here and say, okay, 115 feet is 31%. So apparently my math was correct. Pretty easy.
Mm-hmm.
And that's the straightforward portion of this. It's really not that complicated. I think there's a lot of people out there that want to make this to seem a lot more complicated than it really needs to be. And that's one of the things that bugs me. I think most of this needs to be simple, and it is simple. It's really not as complicated as people want to make it out to be. So all we need to remember is we divide our depth by the atmospheric pressure. Pretty straightforward.
Mm-hmm.
Just remember, the atmospheric pressure is going to be different in freshwater versus saltwater.
33 and 34.
Exactly. Ding, ding, ding. And then what we come up with, we just have to remember that at some point, we're going to have to change it from hydrostatic pressure to atmospheric pressure. We're going to have to go one direction or the other. So in this particular case, 115, because we're talking below the surface, divided by the 33 feet gives us the hydrostatic pressure. Add the absolute pressure of 1, and now we have our actual atmospheric pressure for that depth. We know our safety margin is 1.4 or shallower, and we can do the same thing. If we decide 1.4 is too high a partial pressure of oxygen, we can say, I want to keep all my dives at 1.1. Absolutely. There's nothing in any book that says that's not a bad thing, right?
Especially if you're going to be like diving on top of like multiple dives in a day, and you don't want to rack up your
CNS. Absolutely. Now the good news is, as recreational divers, for you guys to get to the CNS limit is going to be pretty extreme. That's going to be 9 dives in a day that are extremely long and extremely all at 40%. So you're going to have to do a lot of dives at 40% to get anywhere near that CNS toxicity. And we'll absolutely go through that in just a little bit as well. That's going to be part of this class. But you're right, Adam, you're exactly on the right track. So I'd rather give you the truth instead of trying to scare you, right? So, but you're absolutely on the right track. And I love that you're already thinking about that. So good job. I give you the high five fist bump right there. There you go. I love it. So as we kind of go through the same process, you guys got a piece of paper and a calculator handy?
No. Oh, I have a paper. But
I'm a good student. I'm prepared.
Oh my heavens.
Megan gets the A+ for the day. Nice. All she got to do is
I've been taking notes. Good.
Wait, I have my new bin that's full of pins.
Nice.
Thanks to Megan for helping me find the bins. All right, I'm back.
All right, so let's do one together just so we understand this. Megan, Adam, my favorite dive in the world is called the Lady Luck. It is just a fun dive. You can do it as an advanced diver. You can do it as a technical diver. It's just a fun 348-foot wreck. And the bottom deck is at 125 feet.
125 feet?
125 feet. So I'm going to call over to the dive shop for us, and I'm going to go ahead and order us a best blend of nitrox. But what percentage is that going to be at 125 feet with a 1.4?
In the ocean?
In the ocean. Uh-huh.
Okay.
What is the best blend of nitrox?
See, this is where I start to like get
so
all...
4.75 is what we are as atmospheres, correct?
Close. 4.79.
Well, okay, I didn't round it. Yeah, I guess I need to round up, not down. I rounded it down. My bad.
Oh, good.
So we're at the 4.79 atmospheric pressure.
Divided by.
This is where, then we divide it by
9, and then we're gonna. It's the
1.4 divided by 4.79.
Which is 0.29. Did I do that wrong?
You did that exactly right. Good job. That's how easy it is. Now, you can certainly use the chart. You absolutely can use the chart, and the chart will give you the same information, right? So, Megan, my question to you is, if
29%.
we're all doing this dive together, 125 feet, and I do it on 29% nitrox instead of 21% air, how will this affect my exposure to nitrogen?
if you're at 29% nitrox,
instead of 21% air.
you're going to have less, you're going to absorb less nitrogen than you would at a 79% blend.
Absolutely.
Yeah.
Absolutely. Absolutely. So how will that affect my dive?
You can stay down longer.
Exactly. Or if I stay down the same amount of time and come up with everybody else, I'm safer.
Mm-hmm.
Yeah, absolutely. I've got less nitrogen. Ding, ding, ding.
Yeah.
You guys did a fantastic job on that. And usually I have to spend a lot more time on that exact concept. So good job on that. Now, the other concept of that as well, that because I don't think we go into enough idea of best blend. The other concept is maximum operating depth. Now, maximum operating depth is in those tables as well, but the formula, the good news is very similar to what we just went through. We're just, instead of solving for X, now we're solving for Y. So it's still similar math. It's just we're solving for a different portion of the equation. So a couple of ideas just to get out there real quick. Excuse me. 1.4 is the maximum partial pressure for a working load. That's as high as you guys should go in terms of breathing a partial pressure of oxygen. Now, you can go to 1.6, which is the maximum partial pressure at depth, period. Don't go beyond 1.6 because bad stuff happens.
Right.
So you guys want to stay at 1.4, but you can venture into 1.5 up to 1.6. I discourage it strongly. Now, where that changes is when you start getting to that thing called decompression diving. We use 1.6 as our decompression blend because we're trying to come off quickly. But that's really the only good case of using that high partial pressure. Okay, so I just want to kind of throw that out there as well. And I also want to kind of point out as well, you guys have done so awesome that usually this is I'm closing in on being done with the class night 1 at this point. And we've only had an hour. So fantastic. Good job, guys. Made my life easy. So as we kind of go through this, what we want to do is we take 1.4 divided by the partial pressure of the gas in the cylinder. We're going to take away that atmospheric pressure so we get back to hydrostatic pressure because we want to figure out the ATA times 33. So here's how we know that. So if we have a diver wants to know how deep he can dive with a 40% nitrox blend, he takes that 1.4, our partial pressure of oxygen, divides it by the partial pressure in the cylinder, and he gets 3.5. Simple enough. He's going to take that 3.5, and he's going to remove the top pressure because we just want to figure out feet, right? So we've got to get it to hydrostatic pressure instead of making a hydrostatic pressure. So our new atmospheric pressure is 2.5. To figure out how many feet that is in seawater, 2.5 times 33 equals 82.5. Let's go check ourselves. 40%, 83. So they rounded up. I would have rounded down, but that's just me. So 83 feet. At 1.6, same equation, it's 99 feet. That's all there is to it. Does the equation look similar?
Yeah.
Yeah. It's basically the same cylinder. And again, all you're doing is solving for X instead of Y. That's all the difference. That's as complicated as the math really needs to be, guys. I can certainly try and make it more complicated if you want me to, but I think keeping it simple seems like a better way to go, and it's easier to remember. And I can honestly tell you that every time I go on a dive site, I pull out my calculator, and I put and I do this math by hand, I've never once ever used the chart. It's that easy. But understanding how the math works definitely makes your life a lot easier as well. Make sense?
Totally makes sense.
All right. So there is one other law that they touch on just briefly. It's not super important, but I definitely want you to have at least have heard it, and it's called Pascal's law. Now, water pressure changes as the diver swims deeper into the sea. The principle of the transmission of fluid pressure is the basis of Pascal's law. So mathematically, the change in pressure of an enclosed fluid is equally transmitted to all points in a fluid. What is he saying? Here's all he's saying is that as we go down, the pressure will be equal all the way around you. It's not going to be more pressure on your head versus your feet versus your toes versus your ears. Okay. It talks about it very briefly in there in the information, but here's the perfect example of Pascal's law, and this is how it all comes together. I love this little video. I've always wanted to make one of these. This is a Cartesian diver.
Hello, I'm Dr. Bruce DiNardo here in the Physics Lecture Demonstration Laboratory at the Naval Postgraduate School in Monterey, California. How can a submarine sink or rise? One way is to change the amount of water in the ballast tanks. But how does this cause sinking and rising? We can understand the behavior by considering a simple physics demonstration called a Cartesian diver. Here is our Cartesian diver apparatus. It is a flexible 2-liter soda bottle with an inverted glass test tube inside. The test tube is open and it contains some air. The yellow tape around the glass and the cork in the top there is just so that it can be clearly seen in the classroom. The bottle is filled with water and is securely capped. There is enough air to make the test tube float. Without the air, it will sink. There are different ways that you can make the diver sink. One is by telekinesis, using your mind to move objects. This takes effort and practice, so let me see if I can do it. Does anybody have any questions? That you do. While I did this, my hand was on the bottle. Can I sink it without my hand being on the bottle? Let me try. Nope, can't sink it. As far as I know, there's no scientifically documented evidence for telekinesis. I sank the diver before, squeezing the bottle. Unsqueezing the bottle causes the diver to rise to the top. The apparatus may have been discovered by René Descartes, but the first thorough and printed account was in 1648 by a contemporary of Descartes named Maggioti, who claimed to have discovered it. Maggioti was a favorite student of Galileo. To understand the Cartesian diver, we first need to recognize something about fluids, which are liquids or gases. In gravity, a body experiences not only a downward gravitational force, but an upward force in addition. This force is called the buoyant force. The buoyant force occurs because the pressure in the fluid increases with depth due to a greater amount of fluid that is supported above. For example, if you go deep enough in a pool, your ears will hurt due to this increased pressure. The pressure increase causes the upward force on the bottom of the body to be greater than the downward force on the top. The net effect is an upward buoyant force. The buoyant force is quantitatively given by Archimedes' law. The buoyant force on a body in a fluid equals the weight of the fluid displaced by the body. From Archimedes' law, the condition for sinking is easy to remember. Sinking occurs when the average density of the body, which is the total mass divided by the total volume, is greater than the density of the fluid, water in our case. Let me set up a very simple example. We're going to have a glass test tube here full of water. So this is our body, okay? And now I'm going to submerge it in water. Okay? If I release it, what's going to happen? The average density of the body is greater than the density of water because the density of glass is greater than the density of water, and it sinks. We can now explain the demonstration. Look carefully at the air in the test tube. When I squeeze the bottle, you'll notice that water comes into the test tube and compresses the air. The water is incompressible. What compresses is the air. Let's consider the diver to be the glass, the air, and the water inside the diver. The volume of the diver is constant, but when I squeeze the bottle, water enters the test tube, so the average density goes up. Once that average density is greater than the density of water, it sinks by Archimedes' law. In submarines, the ballast tanks are used to increase or decrease the mass while the volume is held constant, just as we have seen with the Cartesian diver. Pumping enough water into the ballast tanks can cause sinking, and pumping enough water out of these tanks can cause rising. The Cartesian diver is an old, popular physics demonstration and toy. The apparatus is simple, and you can make one at home. Googling Cartesian diver yields tens of thousands of results, and there are also many discussions on it in educational scientific journals.
What do you think, guys? What do you guys think? Pretty neat?
It's pretty awesome.
Yeah, the nice thing with the Cartesian diver, it demonstrates a lot of these key principles. It talks about the ideal gas law, and the ideal gas law is really the culmination of everything we've been talking about. It's Dalton, it's Gay-Lussac, it's everything put together into one constant idea. So we put all those together and we add Pascal's law, and now we get a good idea of buoyancy together. So definitely kind of a fun way to look at it overall. Make sense?
Does.
All right. What questions do you have? We've gone over a lot so far.
I don't. For me, nothing. The questions. It's just remembering the. I don't know if they're going to be on the test. Like I can understand the principles and what all the different things. It's just remembering the specific the people according to what laws they have, because like I understand the formulas and stuff, but just remembering.
And if you guys would like, I've got a cheat sheet on the overall laws when we use them, and the law is simply stated that I'd be happy to send you as well. In fact, what I could do, if you'd like,
That'd be great.
Check this out. I could even get it to you right in the chat, private chat. There is your law simply stated. You can just copy and paste that out onto a notepad. And let's see.
Cheat sheet. I love it.
I like cheat sheets. And there is where we use them. So there's your 2 cheat sheets for the day, where we use them, how we use them. So you can just copy and paste those on something nice and easy for yourself. I could email them to you if you'd like as well. So just let me know if you need me to email them. Not a big deal at all. So in scuba, the effects of dissolved gases like Pascal's law principles, pressures applied to the fluids is equally transmitted in all directions to all parts of the fluid. So Pascal's law principle, pressure applied to fluids is easily transmitted in all directions to all parts of the fluid, to all parts of the container. So let's think toothpaste for a moment. So 2 Pascal's law of principles is a fluid distributes the force in all directions equally. An example, hydraulic fluid and brakes. Makes sense? That's how hydraulic brakes work. It's basically Pascal in reverse, right? Overall. So consider this. Hold your hand straight out. You have more air on top of your hand or under it?
Same.
You don't feel a difference, do you?
Mm-mm.
If you go to the bottom of the pool, do you feel the weight of the water pushing you straight down?
The weight of the water pushing me down?
Yeah. You get down to 11 feet in the pool. Do you feel the water on top of you?
No, not really. I don't feel it, but I know that the buoyancy is affected because of my oxygen or lung capacity or the BC.
Absolutely.
The pressure makes it so that I definitely go down, obviously. When you get lower depths, that's why you have to fill your BC with air.
Absolutely. And that's Archimedes, right?
Yeah.
So now let's take that concept a little bit more. So if you dive down 900 feet in the ocean, what would that feel like? Would that feel the same as being an 11-foot pool, or would it feel differently?
Assume that it feels the same. Pressure is the same.
Yeah, exactly. So what it's basically telling you, in summary, is Pascal's law principle, the pressure of water, any fluid, is distributed equally. So if you dive deeper in the water, you feel the same amount of squeeze from all sides around you, not just on top. It's equally distributed across. That's all we're trying to say with that. Make sense?
So my one question, you just help me with this. Air is compressed. It's not, it's just as far as what our body can absorb is the hindering factor. Is that correct?
Correct. Yeah.
Like in the submarine and stuff, like there's air in a submarine and like
they're pressurized to 1 atmosphere.
Squish at depths, right?
Yeah. So inside the atmosphere, that's kind of one of the cool things. And they have these suits out there. They're called 1 atmosphere suits as well. And they're really neat. They look like Mr. Robot from Lost in Space, right? You get in these things, it's a 1 atmosphere suit. You can go to 1,000 feet and they can pull you straight up without any decompression at all because you're at the same atmosphere inside. The reason they're so scary and big is they have to be thick so they can hold the pressure inside without getting squished like a tin can, right? Same thing with submarines. Is they have to be rigid and durable so as they go down that it doesn't squeeze the air inside. That's why they don't have to decompress. It's a 1 atmosphere environment.
Okay. So essentially our bodies are changing the atmosphere with the depths, but in the submarine, we're actually keeping the air inside the space at 1 atmosphere versus our bodies are not.
Well, what we're doing is we're taking on a little a higher partial pressure of air as we go in, and so we're replacing that air. If we just held our breath, our lungs would contract. So we're continuing to breathe in, but what's changing is the space between the molecules and the gas we're breathing. So it's becoming more dense.
Yeah,
exactly. So you're getting it.
Yeah, no, that was something that like I never really understood a little bit because like when you explain that 1 atmospheric suit makes sense. Like same thing with like submarines because they keep the submarine space of 1 atmospheric too, correct?
Exactly. Exactly. All right. So let's talk a little bit about sac rate for a minute, if you wouldn't mind. So sac rate, does sac rate change at 99 feet, 150 feet, 33 feet? Do we have a different sac rate?
Yeah, because our sac rate is because we're using more of the partial pressures in the tank at depth. So is that we're using more of the tank, but like at different atmospheres. I guess the sac rate is the same, just depending on how deep you are.
Sac rate actually doesn't change. So, Megan, what does sac rate stand for?
Your surface air consumption.
Exactly. So our surface air consumption doesn't change. It's always going to be the same. The amount I breathe and the capacity of my lungs is what my surface air capacity is, right? And how fast that it goes through. Does that make sense?
We use the same amount of volume in our lungs no matter what. It's just compressed to depth. Exactly.
Once we get into depth and effort, then it becomes RMV. And that's the respiratory minute value, right? And that's basically what means that's how fast we go through gas at depth. And so a lot of people really get confused when we start talking about sac rate. Man, my sac rate was really kicking butt at this depth. Or my sac rate, your sac rate is a sac rate is a sac rate. Your RMV was kicking butt, yes. And when it comes to RMV, Nikki kicks my butt 3 out of 4 times. Absolutely. It didn't used to be that way. There was a day I remember back one time.
Look at Megan smirking over there.
But now there's that time. She kicked my butt this weekend. That's for sure. My breathing rate was off the charts. I don't know. Something was just off, and so she was beating me by about 8%. So here's what we need to understand: is our sac rate is our sac rate is our sac rate. So here's what I'd like you guys to do. If you guys have access to a regulator and a tank, you think you might be able to come up with that, and a mask?
Absolutely.
What I'd like you to do is
he has all my stuff.
hey, it's right there.
So what I need you guys to do is tomorrow or Friday night for date night, or one of these nights for date night. I want you guys to and take a picture of this. For the love of God, please do this for me. Take a picture. I want you guys to find an episode of Big Bang on Netflix, or I think it's on Amazon right now. And I want you to set up a tank next to your chair. I want you with a regulator on it. I want you to record on a piece of paper how much gas was in the tank before you started. Put your mask on and start a timer and watch a whole episode of Big Bang Theory while breathing from a regulator for the entire time. At the end of, once you've finished up your sitcom, then I want you to write down how much gas was in the tank afterwards. Simple enough. What we want to do is do that 3 separate times. And then what we'll do is we're going to measure the difference. So if I started with 1,000, I ended with 500, that means I went through 500 PSI, right?
Mm-hmm.
If the show was 20 minutes, I divided that 500 by 20 minutes means that I went through 25 PSI per minute. So what I want to do is do that 3 times. And what that'll do is it'll give me my average sac rate. And that's a great place to start to understand what my sac rate is.
Yeah.
Now, once we do that, then we can start getting a little bit more complex. So if I always do my sac rate on an 80 cubic foot aluminum tank, does that mean my sac rate will always be the same if I use a 100 cubic foot tank?
So our sac rate will stay the same. We just have more volume of air.
Exactly, but our calculations will be off.
Our calculations.
Because there's a lot more gas in a 100 cubic foot tank than there is in a 80 foot cube.
Right.
80, exactly. So
we have to calculate by how much air or how many bars in the tank, right?
Exactly. So here's how we do that. And I happen to have a spreadsheet. I will give you a preview of my very coveted. I get 2 to 3 requests a week for people. Will you send me your spreadsheet? Take one of my classes. I will absolutely send you my spreadsheet. I have got weeks into this. It's bad. It's ridiculous how much time I have in this stupid spreadsheet. And I just got done spending another 16 hours in it not long ago. Share screen, window. So here is my crazy over-the-top spreadsheet. And it is a lot of fun because it does a lot of really interesting things. The first thing it does is it'll calculate everything for seawater or freshwater. It'll calculate by depth. So if I'm doing a 132-foot dive for 20 minutes on 21% oxygen, 0% helium at this very pressure on an 11.1 liter tank, starting with 3,000 PSI, it'll tell me that if I have an 11 liter per minute sac rate, that I will end that dive at 193 PSI. So it's pretty crazy. And I'll happily go through more of this with you guys. But here's where it gets interesting: is I have this interesting spreadsheet for tank data, and as we kind of go through this, this is the interesting one to look at. Place to look at is the amount of liters overall. So we start noticing that an 80 cubic foot Catalina 80 has 11.1 liters in it. A CMS LP85 has 13 liters in it. A Catalina HP 100 a Faber 100 HP 100 has 12.9 liters in it. You like the 117s, don't you, Adam?
No, I have your old aluminum. The ones I bought from you was the aluminums, and we bought some neutrally buoyant aluminums from Darren, and then I have a 133 still and then an 80 still.
Perfect. So if you had on that 133 Faber, that's 17 liters of gas. Now that's important because doing this math is a lot easier and more accurate in metric. So knowing that 133 is 17 liters of gas makes your life a lot easier.
Absolutely.
So how does that come into play for you? I'm going to put this presentation up here for you. Take me a second. Oh, it didn't share. Dang it. Okay. I thought I'd shared a screen, and I guess I shared a presentation. Sorry. Here we go. Window. There we go. Okay, so here's how we do this. The first thing we need to do is understand the PSI. We started with 3,000 PSI. We ended at 2,500 PSI. Means we used 500 PSI. Yep. Now let's convert that to bar, which is a metric measurement. 500 PSI times, and I just have this number memorized, 0.06894, means we use 34.47 bar of gas. Okay. Makes this a tremendous amount easier. If we know we had an 80 cubic foot aluminum tank, that means we have 11 liters of gas. All we need to do now is multiply 11 times 34.47, means we used 397 liters of gas. If we use 397 liters of gas during this time, that means we went through 19.85 liters per gas per minute.
Okay.
So it makes it a lot easier. And the nice thing is by doing it this method, switching it into metric, you can literally plug in any tank you want into this. All you have to do is plug in the liters of that tank. So for example, you have those 133s, that's 17 liters of gas. Convert this by 0.06894, and it gives you your bar. Multiply the two, and it gives you your actual liters of gas. Now, where this becomes interesting is we start adding together basic ideas, and we start understanding the idea of effort on our SAC rate and our RMV. So this is actually should be. I'm going to
RMV.
There you go. I've been wanting to add that for several times, and I've just always forgotten to add it. So the effort of a dive is a light, easy dive, very low effort. We'd multiply that by 1.1 to 1.5. A medium effort dive, we're kicking a lot more, 2 to 2.5, and a heavy effort dive can be 3 to 4. If we're in a heavy current in the cold in a dry suit, carrying a camera, that could easily be a 3-time effort. Now, how does that all translate it out? The first time we have to understand our SAC rate and be able to convert that out. The second part is understanding the rest of it overall. So if we're doing a light effort dive, no current, with a 117, 3,000 PSI at 66 feet seawater, which is 3 atmospheres, and we know our SAC rate because we watched Big Bang, we followed what Benjamin suggested, was 14 liters per minute, we can figure out how much gas we're going to go through on just about any dive. Mm-hmm. Here's how that looks. So 117 is 15 liters of gas. 3,000 PSI times 0.06894 is 206 bar. We multiply those two together. We know we go through 3,090 total liters of gas. Now, we're safe divers, and so we want to make sure we don't use that 3,090 liters. We're going to use 2,000 or 2/3 of that, which gives us 2,000 liters. Okay, so that's our usable gas because we saved 1/3 for safety. So all we need to do now is say, okay, 14 liters times a 1.5 effort, because this is a nice easy dive, equals 21 liters per minute of actual usage. Now we add that atmospheric pressure in there. We're going down to 3 atmospheres, 66 feet, times that 21 liters per minute actual usage means we're going to go through 63 liters per minute. Easy enough. Now all we have to do is 63 liters divided by 2060 means at 66 feet, we can do 33 minutes of dive time and not step into our safety margin at all.
Nice.
So that's how we do that.
That's how you plan a dive.
That's how we actually plan a dive.
Yep.
I don't expect you guys to remember all this perfectly, but I will happily go through this as many times as you need me to. And I'll go through this before dives with you as well. And I promise you, when we started the dive guide, we'll be doing this on paper with paper and pencil.
And that's fine. The stuff all makes sense to me. I just got to remember that calculation of 0.06894. And obviously, it's best to do our SAC rate manually, but we have lots of data from our 100+ dives from the Sunto computers too, which is probably not quite as accurate as this.
Yep, it gives you the challenge with taking it from the Sunto is not all your tanks were the same, right? Yeah. And so with this will give you based upon you, and you can apply this to any tank, and you can certainly start getting a better idea by applying this and then going back and checking it to make sure that you're accurate. But what you'll find is the variance for you will be in your effort. Your SAC rate won't change, but your effort will. So you'll start getting a better idea of this was a heavier, harder dive, this was an easier dive, or my mind was in the way. And your mind effect actually takes it and affect some of your effort as well. Right. So like I said, the good news is when we start doing our dive guide stuff, we'll do some of this because I would like you guys to be able to do this for your divers or for a dive with everything together so that you'll understand, hey, I've got this many divers. We're going to go off and do this. Can we do the dive? Really? And you can start doing that predictive idea that, okay, I'm doing an 60-foot dive with 4 divers that have 80 cubic foot tanks. Let's do the math real quick. How long do I think I'll be able to stay down if I figure my average diver has a 17 liter per minute gas usage? So I can start being a little predictive on that. If I plan my gas before the dive, I can say, okay, I would expect that my halfway point should be at 20 minutes. My ending time should be 40 minutes. So I can say, okay, guys, we're going to go on a 35-minute dive. We might get a little bit extra out of it, but I'm going to keep an eye on you. But you can now predict and say, okay, I know that this dive is probably not going to go past 40 minutes because I've got these divers. And when one comes up, we all come up because I got to be with my divers. Make sense?
Yep.
And that's what I talked about a little bit earlier when we talked about becoming a dive guide. Is my job is to teach you to be slightly psychic, right? Prevent problems before they become problems. And one of the easiest ways to prevent problems is to plan for them.
Exactly.
So easy enough. So Megan, I asked you to tattoo a couple of numbers on your body somewhere for Adam to find. For every foot of depth in fresh water, pressure increases by how much?
1 atmosphere. What? Hold on. Restate that question.
For every foot of depth in fresh water, pressure increases by how much? How many psi?
0.432.
Ding, 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 ding. And Adam, in salt water, it was how much?
I don't remember that one. It was I started to write it down, but I didn't have a pen. Say again?
0.445.
0.445.
Or if you watch the screen, I flashed it a few times. No worries. All right. So Megan,
he was on top of the game.
I'm going to give Megan a second. Actually, we got to go to Adam. I'm sorry. Adam, the greatest expansion or compression per foot happens in which depth area? The first 33 feet, 66 feet to 33 feet, 132 to 99 feet, or 99 feet to 66 feet?
The first 33 feet.
The first 33 feet is exactly right. Good job. Way to redeem yourself, buddy. All right. Which physical law?
I don't remember specific numbers sometimes.
It's tough. I believe I get it completely. Megan, which physical law states if a temperature remains constant, the pressure of volume and gas are inversely related?
That is Boyle's law.
It is exactly Boyle's law. Good job. All right, Adam. Here's a tough one for you. The absolute pressure at a depth of 165 in salt water is how many atmospheres?
165. What? I did that wrong. 5 plus the atmosphere on top, so 6. Hey.
6 is exactly right. Good job. All right, Megan. Breathing gas consumption decreases as depth increases, increases as depth increases, remains the same, or varies inversely with depth.
Remains the same.
Your gas consumption.
Oh, your gas consumption. It increases as depth increases.
There you go. Good job.
I still have saccharate on my brain.
You're good. So, Megan, why is that?
Because everything's getting more dense. So you're consuming more, but it's not that your saccharate hasn't changed. You're just consuming more because it's denser.
You got it. Now, they incorrectly termed this question, so we're going to give SSI a pass on this one. But Adam, what is the surface air consumption rate of a diver with a 3,000 PSI rated tank, 80 cubic foot cylinder, who uses 650 PSI in 10 minutes at a depth of 33 feet in the ocean?
I had to do this.
So actually, it is termed correctly. I'm sorry. We're at 33 feet, 650 PSI for 10 minutes.
So we're using hydrostatic, correct? So you don't have to add the extra atmosphere.
You tell me.
Do all this math stuff. I did this question, similar question, probably the same one, but I'm probably going to get this wrong, but is it D, 30 PSI?
It's not. Megan, what's the right answer?
Isn't it 32.5 PSI?
It is. How did you get there?
I just remember that question, honestly. At least
suck.
I'm honest.
You are. Here's how we got there.
This is the one where I got confused, but now having taken your class, so hold on. I'm going to figure this out because if your PSI in 10 minutes is 650 PSI in 10 minutes, I think I can figure this out because then we have our 0.445. So it'd actually be 65 PSI per minute times 0.5.
65
right?
PSI per minute.
65. Well, you're close. So 65 PSI per minute is correct because that's 10 minutes divided by 650 PSI. We went through 60 PSI per minute. Now, remember, we have that.
Half that.
We're at 2 atmospheres now. So we're at 50%. So half of 665 PSI a minute is 32.5.
That makes sense.
There you go.
I was thinking of it more complicated than I should have.
Yep. And I think that's the most common problem in diving and physics is people want to add complexity that doesn't need to be there.
Yeah.
All right. Whose turn is it?
Well, I got it wrong the first time. Megan redeemed me in a way, and then I don't know.
We'll give it to Megan anyway. So Megan, a diver and his or her or their equipment, to make sure we get all the pronouns correct in here, and her equipment weigh 175 pounds and are neutrally buoyant in salt water. To be neutrally buoyant in fresh water, the diver diving with the same equipment, he, she, or they have to add, subtract, move, or all answers are correct.
I know this one.
It's C, remove weight.
Ding, ding, ding. Good job. Why is that, Megan?
Because salt water is denser, so it's going to take more weight to have them go down. Fresh water is not as dense.
And right, like our professor said, that the more dense we are, or the more dense everything is around us, the more dense we have to be to get down. The more dense we have to get down in that, because it's denser water than fresh water, means we have to add weight. So you're exactly right. Good job. All right, Adam, we're getting an A+ today. I'm determined. If 0.1 cubic feet of air is needed in your BC to maintain neutral buoyancy at 30 feet in the ocean, what will happen to your buoyancy if you ascend 10 feet without deflating?
If I ascend,
You ascend.
I become more buoyant.
You will absolutely become more buoyant. Good job. All right, we talked about this one as well, Megan. An altitude of 16,000 feet, the atmospheric pressure is approximately
1/2 the atmospheric pressure at sea level.
You were listening. I'm so proud. Good job. I'm always proud when the students actually listen. All right. I think we might skip this because I've got the answer already on there. So I may come back to that one. So don't be surprised. Hopefully you got to look at the answer.
I didn't get to read the question, so I didn't even know what it said.
So, Adam, if the volume of a gas is kept constant, what varies directly with temperature?
If the volume of the gas is kept constant, what varies with temperature? The volume, so the pressure.
Yeah, exactly. You got it. Good job. All right, 2 more questions. Megan, the partial pressure law, Dalton, requires the sum of the partial pressures to always be equal with which?
The absolute.
Absolute is exactly right. Good job. Adam, assuming you guys already did this question as well, so I don't feel bad skipping it anyway because you already did it, but there's the answer for you. You guys really crushed it when you came to those questions about how to figure that out. So really, really, really great job, guys. Perfect, guys. Well, we are ahead of schedule. You've done a wonderful job on this evening. So just to kind of recap what we talked about, we went through all of the fun and exciting laws that are the laws of Boyle-Marriott. We even talked a little about who Boyle-Marriott was. We talked about Charles' law, which is our boiling pot law. We talked Gay-Lussac, which is the hot air law. And he was full of a lot of hot air if you read his stuff. Anyway, we talked about Henry, which is the law of dissolved gases as well. We even got into a little bit of Pascal, which is a little bit more of an advanced concept. And so we could talk about the Cartesian diver. And we showed in kind of a real idea what Archimedes and buoyancy really was about through the Cartesian diver as well. So I love that as well. We discussed a little bit of physics as well through this process. And we did a lot. This is possibly the hardest section that most people really struggle with. And you guys made it look easy. So good job, guys. We did talk a little bit about gas usage as well as how to figure out your SAC rate. I'm looking forward to getting pictures of you two sitting in front of the TV with your regulators, your masks on, cuddling as a cute little date couple. I think this is just an amazing date night activity.
How many people have you seen actually do that yet?
I've only had one person send me a picture. No, I've had 2 people send me a picture. I had one guy, he had an 11-year-old in the class, and his son fell asleep while doing it. He's got a picture of him with his regulator and his mask on in a chair, just fast asleep. And then I had another one of my students actually put his fins on, which I just love that he put his fins on, and he had his mask on and was sitting in his easy chair. And his wife took a picture of him watching The Big Bang Theory, like I suggested. It was awesome. So I've only got 2 pictures, but I'm looking forward to the date night photo.
Oh yeah, I'll make him do it.
I love it. I love it. So we went through a lot tonight and like I said, I think tonight is the hardest night. Megan, give me 2 things that you learned tonight.
Oh, I feel like I learned a lot. Like, because Adam, I read through a lot of this, and then it was late at night, and then I went back through it, and I was like, I feel like I'm reading a foreign language. I'm like, I know I'm not this dumb, but I think that it is simpler than I think I was making it. So
it is.
Anyways, and the formulas make a little more sense. So I don't know. I learned a lot.
Good. What's one thing other than a lot that you learned? What's something that stood out for you?
I like this the Daltons, like it's just 2 + 2 = 4. You know, it's just all those little pressures combined equal like 1 or whatever it is. You know, like 2 + 2 = 4.
And that's one thing I'm hoping you guys take away from this, that a lot of this physics is not nearly as complicated as people want you to believe it is. These guys with these complicated names like Gay-Lussac's law and the Henry's law, it sounds so overwhelming. It's very Darth Vader-ish or very ominous, right? It's not really all that big a deal, right? Once Vader took his mask off, he was just a decrepit old guy that couldn't breathe on his own, right? So that's really what it is once we take away the scariness of it, it's not that complicated. And the good news is some of the stuff, like with Dalton's, there's 2 charts in your app that you can pull up anytime, and it's already done for you. So now you know how they're done. So good. Adam, what's one thing that's kind of stood out for you that you may not have known before?
That they make 1 atmospheric suits and how it works.
They're pretty neat, huh? If you get a chance, go in and look at 1 atmospheric suits and check them out. And if you get a chance, if you find the right videos, there's actually a thing that they put inside it. There's a bicycle seat strapped in with straps, 4 straps. And so you literally sit on a bicycle seat, and then you put your feet in, and there's pedals for your feet. So you're not actually standing in the suit. You're on a bicycle seat.
That's fascinating.
Absolutely. If I think about it, yes.
The other thing that I learned that I thought was interesting was about how our dive computers can be changed from freshwater to saltwater, because it does make a difference if you were going really deep. It doesn't obviously make a huge difference if you're not doing deep diving, but I thought that was cool because, you know.
That's helpful, isn't it? It's definitely something we don't talk nearly enough about, the variance of that. And it's something we probably should, right? And get a deeper understanding that pressure and that weight absolutely means something. And it's important for us to understand.
Yeah.
Let's see. I was looking for it. I have an interview with one of the first testers of the 1 atmospheric suit. And I'm trying to find her. She was amazing. She does a lot of underwater videos, and I just loved talking to her. She is just amazing. I'm not finding it really quickly, but I was thinking I'd send it to you. Well, I cannot find her. Let's see. Her name is Karen. Not Karen. It wasn't Karen. Gosh, I can't think of her first name to save my life. So I will, when I find that video, I'll send it over to you. Definitely an interesting video. She was super sweet. I really liked her a lot. She shoots videos, and she was the first person to dive the undiscovered islands in Indonesia, as well as she has a really cool film she shot where these elephants would swim 2 to 3 miles across this island. And she has some really cool video of her underwater videoing elephants swimming.
That's
so pretty tripping. She was really, really neat. Nancy McGee, there it is. Let's see. I was blanking on her name. I did a 2-part interview with her. She was super interesting. And let's see, copy. So if you want an interesting interview to watch, this is Nancy McGee. And there's on the thumbnail, there's a picture of her in the 1 atmospheric suit. So something fun for you to check out. Well, good. I'm glad you guys picked up something. I hope this is of value to you. That's all I could hope for. If you guys have any questions, don't be afraid to call, text, write, email, or save them up for tomorrow's class, whatever's easiest for you. I love the questions where you try and stump me. So I promise you, if I don't know the answer, I will tell you I don't know the answer, and I will find out. But I'm getting to the point where that's less and less. So I'm pretty proud of that. The instructors that I've trained so far, they love to argue with me on standards and try and stump me in the standards, and they haven't done it yet. But but I read this a lot, so I'm hoping for the day. I like to be stumped, so I love the challenge. Well, cool, guys. What I'll also do is I'll download this tomorrow and I'll upload it to YouTube for you guys, and I'll send you the link so you can go back through this class as well. And you'll have access. You'll have access to this whole class. So if you thought I said something, you weren't sure, go back through it and watch it again. You're welcome to. That's why I put it up, so you have access to it. To be able to. Did he say that? And then if I said something wrong, then we can go back and prove if I said something wrong. So keeps us all transparent. I love transparency.
No worries. Eventually, I am gonna want to start doing like I want to like start discovering new things, and then most of that kind of stuff is at depth, like wrecks and different things that are deeper than recreational stuff.
Oh, absolutely. I've got the video for you. This is a full deco dive. I've got a 10-minute video that you should watch because it was cool. Yellow. There it is. I did this for the park actually. And there's a deco dive that Nikki and I do in Yellowstone that we won't take anybody else that's not deco certified. That you have to be tech certified to do this. The minimum you can do it is 2 tanks. And honestly, 2 tanks is pushing it, right? You're still not getting the super cool stuff. And you're right as you're finding the super cool stuff, you got to make your turn because you're at that point. But in Mary Bay in Yellowstone Lake, you go out and there's the transverse crater. It's about a half a mile swim out there. And when you drop at about 50, 60 feet. But as you go down to 70, 80, 90 feet, it warms up to 55 degrees. And you start coming across these craters or these geysers that are active. And they'll be anywhere from 4 feet in diameter. I found one that was 40 feet in diameter. That was an active geyser. You'll find thermal beds. There'll be like biological material in there, grasses and stuff. And you'll see vents coming up, live vents. It looks like vinegar coming up. It's hot water coming out 300-400 degrees, and it's kind of comes up. It's really neat. It's a really cool dive, but it is not a recreational dive by any stretch.
This is at Yellowstone, like where you've taken us to see the spires?
No, it's on the other side of the lake. We drive around to Mary Bay, which is the northeast corner, and we get in over there. And it's, like I said, it's a long swim. It's a half a mile swim. It takes us 25 minutes to swim to the drop point, to the starting of the crater. And then, so we drop there because we're usually tired of swimming by that point. I mean, literally 25 to 30 minutes of swim. And then we drop in on the crater, and that's where we see it just absolutely super cool. But you absolutely build up deco pretty fast as well. So because you're diving at 7,600 foot elevation, you build up deco fast. And with the depth we're at and how long we're staying, you build up deco. Nikki and I usually spend about an hour and a half, 2 hours on that dive right now. I think we're going to go try it this weekend. We may save it for the following weekend. I haven't decided yet. I've got some friends that do rebreather. They're coming out with us. But we're probably going to take 3 to 4 tanks this next dive so we can get out and see more. So it'll be 3.5, 4 hour dive when all said and done, if I take 4 tanks.
That's awesome.
So it's when you start getting those long dives, Nikki would tell you her favorite dive that we've done together was 3.5, almost 4 hours in Hawaii. It was just not having to come up, carrying multiple tanks was just amazing. We're always disappointed when we come out at the hour mark. We're like, oh man, it's over. When you come out after 4 hours, you're like, okay, it's over.
You're like, I'm exhausted.
But the nice thing is you're exhausted, you're done, but you've spent all the time you wanted to spend, and then probably a little bit more. And when you come back, you're done. You don't have the desire to go for another dive. This is not a 4 dive day. You go to 1 4 hour dive instead of 4 1 hour dives. It is so much better.
Are you allowed to have boats out there on that part of the lake?
They do. You can absolutely take boats out there and drive off the
So
boat.
we find somebody has a boat and they can just drive us to the spot, and then we can just have somebody stay on the boat.
The trick is having somebody that wants to go sit on the boat for 3 hours while we drop in. And then the cool thing is you can come back up the ledge, and there's several places at 40 feet and 30 feet where you get into carbon bubbler zones. And you'll see that on the video as well. But you'll get in this patch and it'll be like 50 feet by 40 feet wide. And it's just little bubbles everywhere, all around you. It's like being in a fish tank. You hear them because they sound like.
That's cool.
It's an awesome place to do deco at. Just fun.
See, that's what I'm talking about. That's one of the next steps that we want to learn. So at least I do. Maybe Megan doesn't.
Here's how I got Nikki into it is I signed us up for a class. And as we're getting ready to leave for Florida, I told Nikki, hey, I signed us up for a tech class. She said, oh, we're doing tech. She said, yep. When we get to Florida, we're taking a tech class. And she says, okay.
That's awesome.
That's the secret.
That's kind of how this all worked out. Like legit. Like I was like, hey Megan, guess what? We're working on our master divers.
So there you go. That's how you do it. You just sign them up for it. And then, hey, by the way, Sunday, this is gonna be our date. Fun fact for you, Nikki and I's first Valentine's Day as a married couple, we went and got ice dive certified.
That's freaking awesome.
That was our first The night before Valentine's Day, we stayed in a seedy motel in Utah. We got there like 11 o'clock. We left the next morning at like 6 o'clock, went up into the mountains and got ice dive certified for Valentine's Day.
That's awesome.
So, well, perfect. I'm gonna